you can all see my slides. Yes, I see a thumbs up from Taylor. Thank you. All right. So, uh, um, so kind of a brief outline of these lectures. So, I'm giving total 3 lectures here. Um, I'll first kind of just motivate what the problem is. And the problem that we want to understand is, what we observe around us, the hadrons that we observe, quarks, which are the fundamental degrees of freedom in the Standard Model, and QCD, which is the specific theory within the Standard Model that governs these types of interactions. So hopefully I'll give you a flavor for what hadron spectroscopy is and some attempts to understand it via the quark model, and ultimately what the theory that governs all this strongly interacting physics is, and it's called chromodynamics. Um, I should say I'm hoping that I've prepared these lectures to be at kind of an introductory level because not everyone um, uh, is familiar with the ideas of the hadrons QCD and especially hadron spectroscopy. So I would encourage, if I am going too fast, if there is something that is not clear, like really not clear, to ask questions. I wanted to have discussions about some of this stuff. I really enjoy talking about it, as Taylor will tell you. So I'm very open to answering questions, and even if it's offline via email, which I'll give my email shortly that you can see, in order to kind of help facilitate you getting immersed in this stuff. So I'm hoping to not present any too technical derivations or kind of too technical theory. I want to give a broad oversense of what's going on in this field, and give you a flavor, with some kind of theoretical aspects, but hopefully it's enough to where if you've taken undergraduate quantum mechanics, you can at least follow what I'm saying. So that's the hope. But again, if there's any confusions, please ask. I'm very happy to go back and discuss details. Um, so once we go through this introduction, which will take most of today, we'll kind of begin in understanding how to quantitatively define what we see in the hadron spectrum, and that's going to require some scattering theory. So, as you may know, we in particle physics and nuclear physics, we get most of the information that we know about nature from experiments which involve the collisions of particles. The general umbrella of the theoretical construct to describe such processes is called scattering theory, and the primary object of interest is scattering amplitudes. And as you know from quantum mechanics, amplitudes is kind of the things you compute within quantum mechanics, in which if you take some special mathematical operations, you turn them to probability distributions, and that gives you some a probability density of kind of what's going on with your particle or where you can find it or what energy it has, so on and so forth. So these scattering amplitudes are specific types of probability amplitudes, which encode all the information about collision processes. From there, we can get information about the hadron spectrum. And what do I mean by hadron spectrum is kind of the allowed states or particles that can exist within some of these interactions. And I'll go into more detail later on kind of what we observe and kind of how we tease these things out. There's a little bit of, if you're familiar with complex analysis, I won't talk at length about the details of the mathematics behind complex variables, but there's some key concepts that we can use in order to rigorously define what we mean by what is a hadron in some collision process. And when we form these form heavier hadrons or nuclei from the collisions of lower mass particles, how do we rigorously define that? From there, I then want to kind of shift tables and it's like, okay, now we know how to rigorously define all these objects. We know how to look at experimental collisions and get these things out, but that's not good enough. I want to, I'm a pure theorist. I want to calculate these things directly from the theory of quarks and gluons. how do we do that? Well, I'll give you a little bit of flavor of kind of the methods that we use to do that. I won't talk at length about a lot of the details and technical computations that go into lattice QCD. I know there's some lectures by Michael Wagman, and there may be some others later in the school that will touch on some of these aspects. So hopefully you can learn some more cool details that way. But I'll keep it more at a kind of superficial and introductory level. And I'll make some key connections with how we turn um, the types of observables we can get from a lattice QCD calculation, which are very different than the scattering amplitudes and the hadron spectrum that we know in the real world in nature, and how we go through a specific process utilizing the tools of these particles inside a box, which is how we compute them, and turn them into observables that we can compare in principle to nature. So that's my general plan. There's a couple of reviews that may be of interest to you if you become interested in this. One is a review by some collaborators of mine from a few years back, and you can look this archive number up online and find this paper. This is a review article on how to obtain scattering processes and resonances from lattice QCD. This kind of summarizes the last part of my lectures of how we go about doing that. It's a really rather kind of good review. Some of the results in there are outdated at this point. We've pushed, even though this is 2017, this field has progressed rapidly. So there's a lot of new results have been coming online, and some very interesting stuff is going on. However, it's still a great review, and for I think most people here said they were in kind of in late undergrad. Reading this is at kind of a low level is rather enjoyable, I believe. There's also a recent review that I was part of that came out the end of last year and is which looks at hadron spectroscopy from the point of view of scattering theory. So what rules from scattering theory can we use in order to understand the hadron spectrum from both experimental, excuse me, I have dogs and apparently the mailman just came. Excuse me one second. All right, that may happen again. I apologize for that. My one dog likes to set off the other one, and I have cautiously brought treats over to try to make them quiet.
No worries. We didn't. I don't think we even heard it, so no worries.
Oh, okay. All right. So where was it? Yeah. So this review here is kind of talks about a lot of the work that a group I'm affiliated with, JPAC, which stands for the Joint Physics Analysis Center, which is the group of theorists and experimentalists working together on unraveling the nature of the hadrons. And it's a rather nice review. There's the first part of it kind of dictates a lot of stuff I'll talk about in the second lecture and some today on what scattering theory is and how we use it. This one, again, if it should be hopefully kind of a more pleasant read if you're just reading it for fun. If you want more serious aspects of this and the references are very useful to go through. In addition to the lectures I'll be presenting here, I've created a few Jupyter notebooks, which use Python and to kind of talk about some basic features of scattering theory. I won't have time to go through all of these details here. However, I have included a link, which you see here is on GitHub. Ajakura is my GitHub profile. And under RPI Summer School HadSpec, you'll find the lecture, you'll find the exercises in Python notebooks. Essentially, I give some references of useful things. If you're not familiar with complex analysis, there's a brief review on some basics with complex analysis. And I have a notebook, HadSpec X1, on scattering. And then the second one is on Lucier, which is the finite volume connection to lattice QCD. And you'll see there's some sample codes and some plots that you can see and play with. You're free to take it, try it out. There's suggested exercises in here, and I'll kind of show that. I mean, hopefully I have some time later today to show off some aspects of it, so you can get an idea of what's in there. And feel free to play with them. If you have questions, I've attached on each notebook my email up top, the ODU one and the JLab one, either one, you can email me. If you happen to find bugs in it, I would be very happy to know. There have been a few bugs when I first wrote these up that I've been slowly fixing over time that people like Taylor have helped me find. So I don't promise that they work 100%, but they should work almost there. So check them out. I've also designed it to use only modules that come standard with the Anaconda package. So this is like NumPy, SciPy, whatever other Matplotlib. So the basic kind of packages that you would use for Python. And at the top, you'll see which ones I import. So if you don't use Anaconda, you can see which packages you need to install. If you do use it, you should be all set to go. I didn't use any weird package that doesn't that is hard to install or anything like that. So hopefully it's useful to you. All right, so talked a lot about the kind of structure of all this. Let's now get into some of the meat and potatoes, and I want to start talking about the hadrons, quarks, and QCD, and perhaps some of these things are really unfamiliar to you. I hope to give a flavor of what they are. So the first thing I want to start with is spectroscopy itself. So what is spectroscopy? Well, it's if we think about in the original context of understanding light, which is where this all comes from, we're looking at the kind of spectrum or the allowed kind of energy levels of, or energy levels of quantum, but the allowed frequencies, if you think in terms of light, of if white light passes through a prism, or which is a continuous spectrum, or if some specific light from some element passes through some prism or spectrometer, how it separates out into different frequencies and kind of makes up the basis for the contents of that system. So if we think about the hydrogen atom, the hydrogen atom itself is kind of the playground of quantum mechanics. We've learned a lot about how physics works just by studying this simple atom. And spectroscopy is a very useful tool because studying the spectrum really allows us to dive deep and to understand what physical phenomena, what is the content that we see in physical phenomena, how does it work, what is its structure, and so on and so forth. So the hydrogen atom, again, kind of this looking at its spectral properties, so how the frequencies of or how the light emitted from hydrogen gas breaks off into different frequencies, led to discoveries in quantum mechanics of quantum mechanics itself. So if you have hydrogen gas and you have some emitter tube that excites the hydrogen gas, and then beams of light come off it, you can collimate that light through some slit, through some collimator, what have you, to a prism, and that prism will split the light from the hydrogen gas into its different frequency modes, and you can photograph it on some plate and kind of get where what frequencies are dominated by this hydrogen gas. And when you look at the emission spectrum of hydrogen, you see that it's quantized. So I think this is the Balmer series, which is the one in the visible spectrum, which you can learn from chemistry. I don't remember if it's Balmer or Lyman. I think it's Balmer. You see that the spectrum is quantized, where you have, say, red, this kind of red frequency line at 656 nanometers, whatever it is. It's kind of bluish green, blue violet in the visible spectrum. So you see some very peculiar properties of hydrogen, and this led a bunch of scientists back in the early 1900s to think about and try to explain this. And this is where the development of quantum mechanics kind of really took off, because classical physics doesn't really do justice in the sense of giving us a global explanation for observing emission spectrum such as what we see for hydrogen. So when we look at kind of measuring these things to high precision, or to any sort of desired precision, we get a sense of how modern physics was formed. So this led us, again, the Bohr model of hydrogen. We have some proton and some electron orbiting it. So the first sense of getting correct this quantization, this discrete line spectrum of hydrogen itself, which led to the Schrodinger equation, which I just schematically write here as H on psi. Psi is the wave function, which is this entity that just encodes all the information about the hydrogen system. The Hamiltonian H is kind of the governing rules of it. So kind of what's its kinetic energy, what's the potential energy between the proton and the electron. And the Schrodinger equation tells you that you can, if you operate your Hamiltonian operator on some quantum state, so some state of hydrogen, which is what this wave function tells you, you can get out the energy spectrum of this system. And this led to what you hopefully have seen at some point in some form or another, the discrete spectrum of hydrogen, where you have different energy levels, so which are labeled by the principal quantum number n here. And I'm writing the energy in electron volts. I should note here that I will be using natural units. So that's units in which h bar equals c equals 1. Particle nuclear physicists tend to use these units since we live in a world, or since we work with a world that, these are the types of scales that make the most sense for us. So if there's some confusion why, E equals m and then where's the c squared? Well, I set it equal to 1. So anyway, we're measuring the energy in electron volts, and you see the ground state is minus 13.6 eV, which is the usual Rydberg energy. And there's some various constants that come into this. So you have the mass of the electron. Alpha is related to the electric charge. Alpha itself is called the fine structure constant, which I'll come back to, which is just some a combination of E squared divided by 4 pi. It's a useful, what ends up being a useful measurement for the electromagnetic force. And the energy spectrum that you derive from Schrodinger's equation gives you the energy spectrum out for different various quantum numbers. And you can end up predicting then what are the radiative transitions from, say, one state here, the 3p state, to the 2s state, which is going from n equals 3 to n equals 2. And you'll calculate that you get an energy release that is associated with the frequency of this red light, which happens to correspond to what you see in the experimental observations of this 656 nanometers in wavelength light coming out. And so this is a great success. Quantum mechanics, predicts this tower of energy states, which is the spectrum of hydrogen, and it predicts these kind of discrete emission spectra that we see here. So studying the spectrum of hydrogen led to the development of quantum mechanics, which leads to a great description of what we see in nature and feeds back into itself. If you do more precise measurements, you'll find that, these states, which look like they're at the same level here, actually do break up into various different splittings. Some splittings are going by different names. There's the fine structure, hyperfine structure, the Lamb shift, blah, blah, blah. All these extra shifts as you do more precision spectroscopy led to us to refine the theory of quantum mechanics, and this is where the development of quantum electrodynamics and quantum field theory came from, where this energy is not it's kind of the first order approximation to what the energy is. There's higher order corrections, which scale if alpha here is kind of the strength of this electromagnetic interaction between the electron and the proton here, and alpha itself happens to be a small number, which it is in electromagnetism. The corrections are scaling like, wrong way, are scaling like alpha to the fourth, which is why if you kind of do a kind of not as precise measurement, you see you get great agreement with what quantum mechanics has. However, if you really want to get precision spectroscopy, you see that you need higher order corrections, and these higher order corrections then led to the development of the modern standard model of particle physics. So this is where we're at now from this original kind of investigations in the spectroscopy. We have the standard model of particle physics, which describes three of the four fundamental forces we see in nature. It describes the electromagnetic force, which I just talked about from the context of the hydrogen atom and the binding between the proton and the electron. Describes the weak nuclear force, which kind of controls the decay of of, um, of um, one decay mode of the nuclei. So for example, the neutron undergoes a decay, beta decay, and that's governed by the weak nuclear force. There's the strong nuclear force, which is responsible for the kind of strong binding of particles to nuclei, and the only force that isn't really that isn't covered by the standard model of particle physics is gravity. Gravity is very weak, and it, in the context of particle physics, doesn't really play that big of a role. There are people who work on this. I won't really touch on that here. So this kind of nice little table of the different particles in the standard model. You have the quarks, which are the fermions that govern or that make up the hadrons in the nuclei, and they interact electromagnetically since they have an electric charge. They also interact strongly with gluons. Gluons are the mediators of the strong nuclear force, much like how photons are the mediators of the electromagnetic force. You have the leptons itself, like the electron, maybe you've heard of the muon and the tau meson or tau particle, the neutrinos, and there's other force particles like the W and Z boson, which are part of this electroweak interactions. You have the Higgs boson, which probably most of you have heard, which is responsible for giving mass to these particles here through what's a process called spontaneous symmetry breaking. And it was kind of the last piece of the standard model that was needed in order to kind of complete the picture that we had. Within the standard model, there are still some puzzles and things that people are looking for beyond the standard model. For instance, in how the standard model is written now, the neutrinos are expected to be massless. However, we know they have some sort, they have some small mass. So, there's a lot of work done by great physicists who are trying to push the standard model and enlarge it to kind of find a better theory that encompasses more of what we see. So, this is the particle content of the standard model. We can write down what the theory is. However, as you see here, it's a remarkably simple theory, and that has kind of a small amount of content in it. Simple in the sense of going through years of graduate school to really understand all these contexts. It's an anomaly free, which what does that mean? Relativistic quantum gauge field theory. All right, I've heard of relativistic, I've heard of quantum, I've heard of field theory, and varying under these various different groups, and like, oh my gosh. But that's all details. I won't talk about a lot of those details here. Just note that even though there's a lot of technical aspects behind the standard model, for what it predicts and what it describes, which is everything that we pretty much see in the natural world thus far, besides a few things outside of it, which are quite big. Let's not face it, but from what it describes, it's pretty remarkable that such a kind of tight package can describe many of the different phenomena we see in nature. So a little kind of brief onto quantum field theory itself, so we can kind of get towards the interactions of the strong force here. Electrodynamics is probably the most familiar force besides gravity with everyone, and the quantum theory, so the portion of the standard model that describes the electromagnetic forces, is called quantum electrodynamics, which is ultimately a theory of electron and photon interactions. So you can write down the theory. It's this kind of simple little expression here. If you dealt with Lagrangian mechanics, this is the Lagrangian, which kind of encodes all the information of the theory inside of it. So this is the piece of the standard model. And you have different terms that correspond to different physical things. So you have these psi fields here, which is the electron or positron field. You have these kind of F tensor here, which is related to this a variable, which is the photon field, which is the field that generates photons from it. through its quantization process. And you can describe the interactions diagrammatically. So you have these kind of interactions that kind of relate the photon through this D term here. You can relate the photons to the electrons, and you get out an interaction, which I'll write with this Feynman diagram. And this Feynman diagram, you have an electron coming in, interacts with a photon, and the electron goes back out. And this coupling strength of the electromagnetic force is dictated by alpha here, which is this fine structure constant, which is very small. So in natural, it's a dimensionless parameter, and its strength is approximately 1 over 137. So it's a very, very small number. It's like 0.007 or whatever that number is there. So this electromagnetic interactions are relatively weak, which is why this whole expansion in terms of alpha and kind of adding terms successively did a great job in the development of quantum mechanics and quantum field theory in order to kind of refine our theory and kind of add better and better corrections to it. This theory does remarkably well. It's often called the crown jewel of physics, because you can describe various different observables to very, very fine precision. You compute these observables perturbatively. So here we have an example of electron-positron scattering. You can write down Feynman diagrams for this type of process. And these Feynman diagrams are nice pictures that encode a bunch of mathematics behind which you sit down and tediously write down with the various transition amplitudes that go into this big picture. You can put it at in the leading order terms or the next leading order terms, and you can make predictions and compare it to experiment. So here is an example of electron-positron scattering. The differential cross section, which is a probability measure of some collision happening between the electron and the positron. And you see here the red, orange, and other color lines corresponds to the energy, and this square root of S is the center of mass energy between the electron and the electron positron as they're kind of colliding into each other. And you can see the x-axis is plotting the cosine of theta, which is the scattering angle. So as the electron and positron come in, they interact, and then they shoot off in some direction, that direction dictated by theta. And you see the dots here are the experimentally measured differential cross sections, and the solid lines are the theoretical predictions, I think to next to leading order, so up to alpha squared, or at least have terms up to those corrections. And you see it does a remarkable job of describing what we see in nature. And this is just one example of the many things you can describe with quantum electrodynamics. So, it's just one aspect of the standard model of particle physics, and it does a good job. I'm going to be focusing pretty much the rest of the time on the theory that describes the interactions of quarks and gluons in the theory known as quantum chromodynamics. So chromo means color, and there is an associated charge with these quarks here, similar to the electron. So the electron has positive and negative electric charge. Quarks have electric charge, but they also have what's called a color charge, which we call it color for no other reason that there's 3 types of them, and in the visible light spectrum you have red, green, and blue add up to make white light. And we just adopted the name for describing the three different types of color that come with quarks. It has nothing to do with actual light color, but it's just a name that physicists aren't very inventive with names, so that's what we've used. So this theory, it controls everything you see from low energy nuclear reactions to the nuclear reactions you see in stars, and kind of what makes up matter itself. So it's a very important theory. So we can write down the quark-gluon interactions in a very similar way in quantum chromodynamics as we did in quantum electrodynamics. So this theory, which it just goes by QCD for short, looks very simple, just like the electrodynamics one. You have quark fields, which quarks come in these 3 different colors, as I said, red, green, and blue. and it just describes some. There's a lot of math I'm hiding behind the details, but it's the conserved charge of these strong interactions. And there's different types of quarks. You saw there were 6 of them that I showed there. There's up, down, the up quark, the down quark, strange, charm, bottom, and top. So these are the ones that we've observed so far. And people are searching for more quarks and see if they exist. You have the gluon fields, which are encoded in these in this G tensor here. So you have this again an A field, and I'm using this boldface to denote this subtly different feature from quantum electrodynamics, where now you have these 3 different charges playing instead of just positive and negative. So you get again from the interactions of this term here with A with the 2 quark fields, and you get quark-quark and a gluon interaction. And this is governed by the strong coupling, which we call alpha S, S for strong. And there's some other coupling constant G of S, which just makes its way in this theory here. However, quantum chromodynamics is very special because unlike quantum electrodynamics, there are other interactions that exist where you can have the gluons, and this is this extra term here, ultimately interact with themselves. So now you can have 3 gluons interact or 4 gluons interact. So this doesn't appear in the Lagrangian in the theory of quantum electrodynamics, where you have photons interacting. This is a feature of quantum chromodynamics where you have these nonlinear type interactions, and this ultimately gives rise to the fact that the strong interactions are called strong because the interaction strength between quarks and gluons is very, very strong. And if we look at a plot of the coupling, the strong coupling at very low energies, so the mass of the proton is roughly here on this scale. There's some heavier particles indicated. You see some measurements of what the strong coupling constant is for very high energy transfers in some different experiments. And you see here that as the energy goes low, so if we're talking about low energy phenomena, so the phenomena of nuclei and hadrons, this strong coupling constant, or this strong coupling blows up. So if you remember, the electromagnetic coupling was very weak. 1/137 was the strength. So adding different terms to in this perturbative series gave you a better and better correction description for some observable. However, here the coupling is not small; it's very strong. So we don't even know how to write a perturbative expansion where we're adding small corrections to this. And this gives rise to the fact that we don't know how to compute low energy hadronic and nuclear observables from QCD itself with pen and paper. There are ways around it, and lattice QCD is one of them, but the traditional ways of using perturbative expansion as you would in quantum electrodynamics do not work. And moreover, this leads to the fact that we don't observe free quarks themselves. We don't actually observe quarks. We observe them combined into some composite object called hadron. So I keep using this word hadron. What is a hadron? A hadron is some bound state of quarks and gluons together. So the proton itself is an example of a hadron where it is made up of quarks and the gluons interacting between them. So we observe protons. They're at very low energies. 1 GeV is their mass roughly. And at these scales, calculating the proton mass from the ingredients of the quarks and gluons is very, very difficult. Lattice QCD is a way to do it, and I'll touch upon some of those things later. So let me stop there. Are there any questions? Am I going too fast or too slow? No comment. Trying to see if I can see if there's any. Okay. All right, so I'll continue then. So now we want to look at, so I kind of, we started talking about the spectrum of hydrogen, developing quantum mechanics and quantum field theories to the standard model of particle physics. There's this quantum electrodynamics, which describes those types of interactions. Then we moved on to the theory of strong interactions called quantum chromodynamics. But now I want to back out and talk about hadron spectroscopy, which I won't go through the history of how hadron spectroscopy helped lead to the development of quantum chromodynamics, but in much the same way it did help. But now we're kind of just take at face value. It's like, okay, we have this theory. What do we actually observe? So we observe hadrons, and the hadrons we observe come from various different reaction processes. So here I'm showing two different types of hadrons. One is a pion, which the pion is a meson, which is made up of one quark and one anti-down quark, as its kind of valence quark structure. And you have the proton here. So you take a pion and a proton, slam them together, and what do you get? Well, you get out, much like in the same way when you take your beam of light and hit it on the spectrum, and you kind of break out the spectrum of the hydrogen atom. We get the spectrum of what happens when you take this pion and hit it on a proton. And here is a measurement of the differential cross-section for pion-proton reactions. There's a measurement of the momentum of the pion on the proton target. And you see various different features. You see peaks and dips in the spectrum. These peaks are what are usually what we associate with as particles. So when you take a pion and you hit a proton with it, it combines for a short amount of time and makes a new particle. This example here that this thing is making here is called the delta resonance, or the delta hadron. So it makes a delta particle, which doesn't live forever, then decays back into the pion and proton. And you see various amounts of these different bumps and some general features of this pion nucleon spectrum. The nucleon here is just a catch-all term for proton or neutron, but here shown specifically for proton. So you see here this peak, which I say corresponds to the delta baryon, which is just another kind of class of these baryons and that we observe in nature. There's another famous one. It's called the N-star 1440, which, if you're not too familiar with, is just one of these other types of hadrons we observe. But you see here, it's not associated with any strong peak. There's a lot of work that goes into analyzing the spectrum and get out what its spectral content is. And the spectral content of these nuclear or hadronic reactions gives us what new hadrons that we can observe. So when we do that experiment and do a bunch of analysis after collecting all that data, we get out kind of what a spectrograph. Here in blue are the delta baryons, and here in red are the excited nucleon baryons. So the proton itself, you have various different quantum numbers associated with the spin. That's what this J symbol here is for. It's for the spin of the hadron. P is its parity. And you get a tower of states, much like we did for the hydrogen atom. And the state here corresponds to the mass of the particle itself. And these kind of widths here are showing the uncertainty we have in measuring the mass, because it's very difficult to do, especially for the higher mass states. So, we do our experiment of pion, just some strong hadron, hitting a proton, another strongly interacting particle, another hadron, and we get out another spectral plot. We want to understand this plot. We want to understand how this emerges, especially from QCD itself. So how do we make sense of this thing? Well, let's go into how we start classifying these things. Hadrons are classified by a set of conserved quantum numbers, which for the hydrogen, it's for again, I'll keep going back to the hydrogen atom as an example. So the hydrogen atom, you have different quantum numbers that describe that system. You have the principal quantum number, which is this n variable that tells you kind of which state you're at. You have the orbital angular momentum, between the electron and the proton, and various other quantum numbers that describe the system here. For hadrons, you have something similar. You have the spin of the hadron, so just what's its spin angular momentum. The parity, how does it look if you change, if you do a reflection about a spatial axis. It's charge conjugation, which is does the particle go to its antiparticle if you change the signs of its charges, or does it become itself? So the pi plus meson, which is a specific pion, it's got positive charge. If you act charge conjugation on it, it becomes the pi minus meson. However, the pi zero meson, which is a charge neutral object, when you act charge conjugation, it just becomes itself. So, what's its behavior under that type of conserved quantum number? You have isospin and strangeness, which are other conserved quantum numbers, which I won't go into much detail about. And you can organize when you start observing these hadrons, which are generally broken up into two different classes. So there's the mesons and there's the baryons. The mesons are such that their spin angular momentum, their intrinsic angular momentum are integer. So you have 0, 1, 2. Mesons are a type of boson. So bosons in general are particles with integer spin. Mesons are strongly interacting particles or hadrons with integer spin. And you have the baryons, which have half integer spin. So 1/2, 3/2, 5/2, so on and so forth. And some examples here, you have the pion, the kaon, and the eta meson are examples of mesons. They all have integer spin. In this case, they all have spin 0. The baryons, you have the proton, the neutron, and the delta. The proton and neutron are both spin 1/2 particles. The delta is a spin 3/2 particle. With these quantum numbers, you can organize the observed hadrons into multiplets, which is just some kind of characteristic organization that describes these hadrons. So for the mesons example, for the pion, kaon, and eta, they organize themselves if you plot these different quantum numbers. So we're looking at JP is 0 minus, so these are pseudo-scalars. Scalars just means spin 0, spinless particles. Pseudo corresponds to the parity being negative. If they were true scalars, their parity would be positive. So the kaons have a strangeness quantum number s equals +1 or -1, depending on if it's the kaon or the anti-kaon. And strangeness is a quantum number that tells you how many strange particles you have, essentially. The pion and the eta have strangeness 0, so there are no strange quarks in there. You have Q on the diagonal, which is their electric charge. So the K plus and pi plus are both positively charged. You have the neutrals here and the negatively charged here. And the different colors correspond to different isospins, which isospin, as I said, it's a strongly interacting quantum number, which is really just how the quarks transform amongst themselves. So great, we have some organizational structure starting to appear just by looking at a conserved set of quantum numbers. Is there anything else we can get from this? So let's look at a specific sector, which is the light isovector mesons. So isovector means I equals 1, and the meson spectrum looks like this. You have the different JPC, so C is the charge conjugation, J is the spin, and P is the parity. Different JPC quantum numbers on the x-axis, their mass on the vertical, and you have different particles, which you may or may not have heard of. The pion is here. You have the rho meson, which is a famous meson that decays into 2 pions. It's here. You have some other particles here. This, the width in this here corresponds to what's called the decay width. So many of these hadrons here, if we they don't live long. They decay under the strong interaction, especially these higher mass ones. And the decay rate, which is really what's given by this gamma here, is equal to 1 over tau, tau being the lifetime. So if you have a shorter lifetime, you have a larger width. So these particles are very short-lived. So how do we have this structure of the isovector mesons. We looked at some examples of looking at the conserved quantum numbers to organize them. We can introduce quarks as building blocks. So we know quantum chromodynamics has quarks in the theory to describe them. Historically, they were developed as a means to try to organize the structure that we see from the hadrons themselves. This introduction of quarks, I'll call it the constituent quark model, because I won't use QCD directly. I'll just use kind of a gross qualitative assessment of how the quarks combine to make up the observed hadron spectrum. So if we look at the mesons themselves, we need a quark and an antiquark. The quarks have spin, they're fermions, they have spin 1/2. So if you have the antiquark spin one way and the quark spin the other way, and then you have in this kind of classical picture, the quark and antiquark orbiting each other with orbital angular momentum L. And the set of quantum numbers we can use to describe this are n, some principal quantum number, L, the orbital angular momentum, S here in this funny combination, which is the spin angular momentum, and they combine together to give you the total angular momentum of the system. So much like if you have different angular momenta, they can combine together to give you a total angular momenta. So in this kind of crude picture of how quarks combine, we can write down a wave function. So nasty equation, but I write it to kind of introduce some ideas here. If you have a quark and an anti-quark together, with sigma being their spins, if you've gone through quantum mechanics, you know that spin, you can, if you have a particle that has spin 1/2, if you measure it along the z-axis, it can either be plus 1/2 or minus 1/2. This sigma is dictating whether or not it's plus or minus 1/2, the sigma and sigma bar. You have a spherical harmonic here, which characterizes the orbital angular momentum structure or wave function of the quark antiquark system. You have some radial wave function, which in a typical kind of potential model approach that you do in quantum mechanics, you would take matrix elements of this thing and use the Schrodinger equation to find what the radial wave function is here. Here, we don't need it specifically, but that's what people would do back in the early days in order to try to get some dynamical information out. You can combine the spins of the quark and antiquark to a total spin here. This is this S value. Then you can take the S value and the L value and combine them again to give a total J value. These things are Klebsch-Gordon coefficients, which if you've gone through all the kind of mathematical rigor to describe how to combine angular momentum, you may know these things. If not, they're just some coefficients that describe how to combine these different angular momentum together. So we have our essentially our meson state, which is a QQ bar system in terms of the individual Q and Q bars with some various couplings to combine everything together to conserve quantum numbers of interest. And if you go through the work and you take this wave function and look at kind of the behavior of these things here, the orbital angular momentum is quantized, so the allowed values are 0, 1, or 2. Two spin 1/2 particles can either anti-align when they combine to make S equals 0, which is called spin singlet, or they can align together, so 1/2 plus 1/2 is 1, and this is the spin triplet state. And then when you combine L and S together, you find that J is also an integer that takes values between the absolute value of L minus S to L plus S. And then also, if you act the parity and charge conjugation operator on this thing, you find that they take on this value here. So if you know a bit about all this kind of terminology I've said here, I encourage you to take this wave function here and apply these operators on there and see what you get out. And you should find that these combinations come out naturally. Nonetheless, with this simple picture of how to take quark and antiquark together and combine them, we get out some relationships between these different physical quantum numbers, and they give us some constraints on what's allowed for what we see. So if we look at this here, this is our original spectrum plot and the different quantum numbers that you can construct. If you have L equals 0 and spin singlet and spin triplet, you can define JPC quantum numbers like 0 minus plus, 1 minus minus, 1 plus minus for L equals 1, and so on and so forth. And if you take time to start mapping out the quantum numbers you see here to the quantum numbers you see here, you start seeing some patterns to emerge this way. So you see the 1s state, so 1 here corresponds to the principal quantum number. would generally think to describe this pion and this rho meson. It doesn't really do that great of a job, you would say, but these are the two ground states, and we're kind of doing a rough gross model here. So, it's kind of crude. But you see for the higher states, you start getting some patterns to emerge. So the 2s state, you get these different 0 minus plus and 1 minus minus, which corresponds to these two here, correspond to this L equals 0. And yeah, they're roughly the same mass here. So you think, okay, this kind of makes sense in this context of the hydrogen atom where you had different states at roughly the same level. You get the 1d states corresponding to these quantum numbers here, and you get the 1p states grouping together in this way. So you see kind of gross features popping out of this. If you want to try to refine this quark model, you put some potential in and put some breaking effects that could kind of cause these splittings here, this big splitting here. You'd have to try to find the reasoning why. And there's a lot of work that was done, especially in the early days of hadron physics, to try to describe this. But you see that if you go through this exercise, there's a set of quantum numbers in this JPC that are not allowed. These forbidden quantum numbers, say 0 minus minus, 0 plus minus, 1 minus plus, are called exotic quantum numbers, spin exotic quantum numbers, because they don't come from this conventional quark model. However, experimentally, we observe states that fit into quantum numbers associated with 1 minus plus. So we see immediately here that this quark model picture, this naive kind of some first approach to describing the hadrons, breaks down. So we need to do better because we want to be able to describe all the states we see by these quarks and ultimately the gluons that come from quantum chromodynamics. And that's the answer here. Is the simple quark model doesn't do it justice. You need to invoke the full power of quantum chromodynamics in order to get to try to describe these states. And that's what people have been working on, especially the past 20 odd years, using lattice QCD as the primary tool to really get at going directly from QCD to what we see here. There have been more experiments, especially in the past almost 2 decades now, where we've been finding states that don't fit the conventional quark model still. And if we look at the what are called Charmonium states, so that is a charm quark and an anti-charm quark, we get again some spectral plot from the experimentally observed hadrons. And in 2013, we started seeing all these new different states, red and blue states I show here. And in old-fashioned quark type models, you would get a good description of low-lying states, but these states weren't found. So this has kind of generated this new need for, can QCD allow for these non-quark model type hadrons? What is the nature of these states, and how do we go about finding a global explanation for these? So kind of the traditional picture from the quark model is that you have mesons, which are quark anti-quark. Anti-quarks I'll do with this kind of red and white circle here. You have baryons like the proton. You have baryonic molecules, which are nuclei. So nuclei are, like the simplest nucleus we have is the deuteron, which is a proton and neutron, which are loosely bound together by the residual strong nuclear forces here. So we'll call that a baryonic molecule. And this is kind of what we understood QCD to be. However, there could be many other exotic features. And when I say exotic, QCD, it may be perfectly fine for these to exist in QCD, but the word exotic is kind of a catch-all coming from these old quark model days where a simple picture doesn't really fit the description. So can you have mesonic molecules? So two mesons loosely bound together. Can you have tetraquark states? Why do we stop at 2 and 3 quarks together? Can there be tetraquarks? Can there be pentaquarks? In fact, relatively recently, probably 10 years ago now, a pentaquark state was found by an experiment at CERN, LHCb, which is LHC and then the B stands for bottom, where they found a state consistent with 5 quark, 4 quarks and 1 anti-quark combinations. There's hybrid states which could exist, and these states I showed here, this 1 minus plus is a hybrid candidate, where it's composed of QQ bar type meson, but then there's some active component of the strong interaction of the gluons binding together to give extra angular momentum that gives these types of quantum numbers. So QCD in principle allows for all these exotic states. So, do we understand QCD? If we do, we should be able to get these things out from them. So this has led to this kind of new age, new hadron spectroscopy. So the goal that us theorists have is to connect this very simple picture, this very simple theory of QCD, to what we observe in the hadrons here. And in order to describe these hadrons, I said, these hadrons aren't just stable particles. I said they decay. So the rho meson, as I said, decays into two pions here. The A naught decays into an eta meson and a pi meson. All these higher states here decay into lower mass hadrons. We need to be able to rigorously describe these hadrons as well as just the kind of simplest pion or proton. So we need a non-perturbative approach to do that. That's lattice QCD. And we need a rigorous way to kind of quantify these hadrons. And that's where scattering theory comes in. So I see it's already 4:20. I have till 4:45, I believe, correct? I don't want to bore people as well.
Yeah, that's right.
Yeah, so maybe let me pause here and see if there's any questions. Any questions from anyone? Don't be shy.
So has there been any discoveries on the properties of those, or for example, that 5 hadron quark, pentaquark? Yeah.
So that's a good question. So these aren't just kind of concocted states that could exist. Some of them are, some, but so for example, the pentaquark, which goes by the name of PC, PC like 4,450 or something like that, which just dictates its mass. Yeah, so we've been able to measure the mass of the particle, its spin. So many of these JPC quantum numbers, its mass, some decay properties, and a lot of these states in the Charmonium sector are thought to be tetraquark states or mesonic molecule states. So for these states that we're finding here, we are finding some properties about them. So kind of its spectral properties are primarily the ones we've been finding so far. So what its masses, decay widths, or lifetimes, spin, parity, charge conjugation, so on and so forth. What is the more interesting thing, which I would say, and I'll say this and others may not agree, is we don't really understand the substructure. So, some states, like the pion, really lend themselves to interpretation of a tightly bound QQ bar meson. Some states, like the proton, really lend itself to a very tightly bound 3-quark baryon. Some states, like the deuteron, through various studies over the many decades it's been looked at, really lend itself to the interpretation of its lightly bound baryonic molecule. Some of these other states, though, it's not as clear cut and it's not as well known. So there's a lot of work that I myself and some of my collaborators are doing, which is trying to come up with observables that we can compute and hopefully one day then compare to experiment in order to get at information about its substructure. So things like that would be like its radius. So, a lot of these things are electrically charged, and there's some quantity called the charge radius. And the proton itself has a well-measured charge radius. And there's been some kind of discrepancies around that recently, but there may have been resolved, according to some. So if we can measure the radii of kind of these more exotic particles, we can maybe start putting some constraints on, okay, if the radius is big, we'll call this thing a mesonic molecule. If the radius is small, it would be more tightly bound, so it's a tetraquark-like state, or a pentaquark state, or a kind of loosely bound baryon and meson. So a lot of those more substructure observables haven't really been looked at yet. They're very hard to get experimentally, and they're even harder to get at theoretically. However, there is work on both fronts to try to push that. And in lattice QCD and using lattice QCD, effective field theories, and scattering theory has given us using these tools has given us at least a pathway for how we could in principle do this theoretically and start coming up with substructure observables. So it's a long-winded answer to say yes, some properties have been measured, but the interesting ones that give you kind of to differentiate between this picture and this picture, I would argue still aren't there, and there's plenty of work to be done. I hope that answered your question.
Yeah, thank you.
You're welcome. Are there any more questions? You're not. So let me briefly kind of go through the ideas of scattering theory on how it's used in order to quantify these short-lived hadrons, and then we'll start back up with that again tomorrow, and I'll kind of move on to these Python notebooks to try to illustrate what they're doing. So all our knowledge from the hadrons comes from scattering experiments. So we have, in the example of pion protons, you have a pion coming in, proton coming in, they interact, and the pion flies off and the proton flies off. So how do we quantify such a process so we can kind of take this measurement here and get at something, rigorously? So in quantum mechanics, we want to take matrix elements of operators, and the operator of interest here is the scattering operator. So these matrix elements are called S matrix elements, and you can think about if you have some incoming state, say pion and a proton, you have the S matrix here, which encodes all the underlying interactions of the theory. And then you want to take matrix elements with the final state, which in this case could be a pion and proton. And these type of matrix elements give you probability amplitudes. These probability amplitudes can in turn be fed through the process in order to make probability distributions, which is where you take the modulus squared of it, of the probability amplitude, to get the probability for some initial state alpha to go to some final state beta. And in principle, the S matrix we can write in terms of some exponential of the interaction potential that's integrated over all time. And this, if the interaction is small here, we can do expansions of the S matrix in a small coupling parameter. This is exactly what's done in quantum electrodynamics. The interaction potential is proportional to alpha. Alpha is small. We can use Taylor expansions of the exponential in terms of this alpha parameter and get out higher order corrections to this S matrix to compute S matrix observables for these different probability amplitudes of the reaction. In the strong interaction physics, this is not perturbative. And in fact, the states here are hadrons, since those are the things we observe, and the interaction potential itself is in terms of quarks and gluons. So it's very complicated. Not only is it non-perturbative, but the non-perturbative nature is such that the asymptotic states, the states in which you're actually interested in, this alpha and beta, are not the states that are part of the theory inherently. They're an emergent property. So this is the mathematical object we want to get at to describe the reaction. And our goal is to fill in elements of this S matrix. So here, if we have a reaction with some incoming on the horizontal and outgoing on the vertical, you would have some interaction of, say, a pion and eta coming in and a pion and eta going out. And this kind of crude matrix here, we want to understand what this yellow kind explosion is. And there's two ways to go about it. One is, can we calculate it purely from theory, like in quantum electrodynamics, or some other way? And with lattice QCD and scattering theory, there is a way to compute this S matrix element. Or can we infer some information about the S matrix element by measuring some cross section, some experimental observable, and get out what is this probability amplitude? So that way is more the phenomenological route. The other way is more of a theoretical route. Both ways are necessary in order to make progress in this field. As you increase the energy, these particles are relativistic. Relativistic systems allow you to produce particles, E equals mc squared. We can transform energy to mass. And now you can have a case where the matrix itself is actually a matrix, where you can have an eta pion go to an eta pion, but it can also go to an eta prime pion. The eta prime is just a heavier cousin of the eta meson, and you have a matrix of different S matrix elements depending on what your incoming state and outgoing state are. You'd also have a case, we've been talking mostly about two particles here, and I'll stick to these lectures on two particle scattering, but you can have more than two particles. You can have three particles. Let's say you have 3 pions come in and 3 pions go out. Well, that gives you a specific S matrix element that you want to compute or either infer, and you have all the different crossed elements here. So once we have the amplitudes, how do we get the spectrum? So I showed you these states in this kind of tower of different energy levels. How do we associate that with this S matrix element? We haven't talked about how to convert this reaction probability amplitude to actually states of the theory. And the key idea here, and this is where some complex analysis starts bleeding in, the key idea is that particles are associated with pole singularities of scattering amplitudes. So if you have a pion, just a free propagating pion, the S matrix element is quite simple because you just have a pion go into a pion, and as a function of the pion's energy, it goes like 1 over E squared minus M pi squared. So the S matrix element, as the pion, if it's a real pion, will exhibit a pole at the pion mass. So as a function of energy, the S matrix element diverges at the pion pole, or at the pion mass, which is called the pion pole. And no, I'm sweeping many details under the rug, but I want this at least today to be a more qualitative introduction. So for a stable hadron, and the pion is not stable, it decays via the electroweak force. But if we imagine turning off the electroweak force, so turning off electromagnetism, turning off the weak nuclear force, which is what we actually do in lattice QCD calculations, or at least what you can do, and think about just the strong interactions of QCD. The pion is a stable particle; it doesn't decay, and it is this pole singularity of this amplitude. If we now think about a more complicated particle, one that is unstable, unstable particles are called resonances, and they are poles of this S matrix in the complex energy plane. So, for example, the rho meson, which decays to 2 pions, can be found as a resonance of pi-pi scattering. So if you have 2 pions, which form a rho meson that go to 2 pions, the reaction, the scattering matrix element roughly looks like 1 over this expression here, where you have the mass of the rho meson, and then you have an imaginary part. So I is the square root of -1. And this imaginary part is proportional to the decay width, or the inverse lifetime of the particle. So here's a little cartoon. 2 pions come in, they form a rho meson, which lives briefly and then decays away back into 2 pions. So on the plot here, the S matrix element, if we take the modulus of it, it won't look like a pure divergence, like in the stable particle case. It looks like a bump in the S matrix element. And the mass of the particle roughly corresponds to the peak of the bump, and the width, the decay width of the particle roughly corresponds to the width of this shape here. So this is how we quantitatively define what hadrons are in a scattering process. They are pole singularities of these amplitudes. And I think I'll stop here. We'll pick up tomorrow with this idea again and start looking at more details of scattering theory and some examples of different types of poles that you can find, which correspond to the different spectra of the hadrons. Let me to here real quick, and then we can go to more questions. So here are the Python notebooks that you'll find on GitHub. As I said, complex analysis becomes a very big player. And if you want to give your hand at these exercises, I'll kind of take you through what they do in the next 2 days with some examples I'll be taking for the lectures and showing them off. I won't talk about the complex analysis one, but if you're rusty or you're not sure, take a look at this one. But essentially, in these, I have some references that are useful, what libraries we'll be using, a brief description of kind of what the task is for this specific little module, some examples for you to try. So in this one, it's just plotting a complex function with Python. Very simple, not need to do much intense computation. And you're plotting the real parts and the imaginary parts and so on and so forth. And then some sample code. And this is the general structure of these Python notebooks. Tomorrow, we'll start talking in more detail about the scattering amplitude, in which we'll talk about processes like the one I just showed, where you have these resonances appear in the scattering amplitude. But this is generally the feature. There's some description here, some plots to see, some code that you can play with and change values of. And if you have any questions, please email me, and I'll try to help you out. I just wanted to share that to make sure that you guys, that's the general structure of these Python notebooks. Nothing here is mandatory, so at your own will. All right, so are there any more questions in the remaining time? I probably went a little over from what I should have. I apologize.
No, great. Thank you, Dr. Jakura, for this great talk. So I'm going to go ahead and stop recording now, and that way we'll open up for questions.
Okay.